Linear transformations are extremely useful in many applications of linear algebra, from computer game graphics to digital signal processing. But then we need to be able to explain to the computer what is a linear transformation and how does it work. For example, we need to tell the computer how exactly to perform rotations. And this is a non-trivial task. The key to solving this problem is the following observation. A linear transformation is determined by the images of basis vectors. So this means that if we know what a linear transformation does to basis vectors, then we can tell what the same linear transformation will do to any vector. So let's consider an example. So suppose we have T, a linear transformation from R2 to R2, such that T transforms the first basis vector 1, 0 into a vector 3, 2, and it transforms the second vector 0, 1 into the vector 1, 5. Now, so question, so what is T of, say, 4, 3? Right, and here we should say that this is a linear transformation. So the idea to answering this question is the following. So what we can do is we can write 4, 3 as a linear combination of basis vectors. So this is 4 times 1, 0 plus 3 times 0, 1. But then we know that a linear transformation transforms linear combinations into linear combinations. So this means that T applied to a linear combination 4 times 1, 0 plus 3 times 0, 1 is equal to, by the properties of linear transformation, to 4 times T of 1, 0 plus 3 times T of 0, 1. And these values, so the images of basis vectors, are given to us. So we know that 1, 0 is transformed into 3, 2, and 0, 1 is transformed into 1, 5. So this tells us that here we're going to get 4 times the image of 1, 0, which is 3, 2, plus 3 times the image of 0, 1, which is in this case 1, 5. And then we calculate the answer. So here we have, in the first component, it's 12 plus 3, so that's 15. And in the second component is 8 plus 15, that's 23. And so here we get the answers that T of 4, 3 is equal to 15 and 23. So this tells us that if we store the values of the images of basis vectors, so then this information is enough to uncover what are the images of any vectors when we apply this transformation. A convenient way to storing images of basis vectors under a linear transformation is to use matrices. And so let T be a linear transformation from Fm into Fn. So let us write down the following mantra. So to form the matrix of a linear transformation, place the images of basis vectors as columns. And so here it's important that we store images of basis vectors as columns. Now let's consider an example. So determine the matrix of a linear transformation T from R2 to R2, which is the reflection in line y is equal to x. So here is the picture of this transformation. So here we have an R2 and the line y is equal to x. And then for each vector u, we consider this line as a mirror. And so then we reflect this vector in with respect to this line. And then, so here we get the vector t of u. Now, how do we find the matrix of this transformation? To obtain this matrix, we have to find images of basis vectors. So what happens to the first basis vector? So this vector is here. So this is the vector 1, 0. Right? And when we take its mirror reflection, so then it goes here, and we see that it reflects to the second basis vector, 0, 1. So this means that the mirror image with respect to line y equals x of 1, 0 is 0, 1. And so because this is a mirror reflection, so the image of the second basis vector, 0, 1, is the first basis vector, 1, 0. And so now we can form the matrix of this transformation. So we place images of the basis vectors as columns. And we should preserve the order of these columns, right? So the columns should be listed in the same order as the vectors in our basis. So this tells us that the first column is 0, 1. And the second column of this matrix will be 1, 0. And so this is, we get the matrix of this reflection. Let T be a linear transformation from Fn to Fm. So what is the size of its matrix? Now, let's recall our mantra. So we put images of basis vectors as columns. Now, how many basis vectors do we have? So in our space Fn, we have n basis vectors. So this means that so the matrix A has n columns. Now, what's the size of each column? So how many components each column will have? So each column is an image of a basis vector. So this means that this image occurs in the space Fm. And so this means that each image has m components. So since we have that each column has m components, so this means that this matrix must have m rows. So we conclude that the size of the matrix, so A has size m by n, right? So m rows and n columns. Now, suppose we are given a matrix A of linear transformation T. Right, and let's write down this matrix. So A is the matrix A11, A12, A1n, A21, A22, A2n, and AM1, AM2, AMN. Right, so suppose we are given this matrix. So how do we find how to determine T of applied to a vector C1 to Cn? Right. So what we do is we use the properties of our linear transformation. So we say that T of C1 Cn is equal to T of a linear combination C1 times the first basis vector E1 plus Cn times the last basis vector En. Now, so because this is a linear transformation, the result is C1 T of E1 plus Cn T of En. Now, how do we calculate this expression? So here we recall that the image of the first basis vector was encoded in the matrix as the first column. So this means that T of E1 is the first column of this matrix. So what we get is we get C1 times the first column, A11, A21, dot, 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 AM1, plus dot, 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 and T of En is the last column of this matrix. So we have A1n, A2n, dot, 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 AMN. And, but this is, we recall that this is nothing but multiplication of a matrix by a vector, right? So this is exactly the product of matrix A with the vector C1, Cn, right? So another way to seeing this is to just compute all the components, right? So here, let's look what's the first component. So the first component is A11 times C1 plus A12 times C2 plus A1n times Cn. The second component is A21 times C1 plus A22 times C2 plus A2n times Cn. And the last component is AM1 times C1 plus AM2 times C2 plus AMN times Cn. Right? So this looks exactly like a substitution of this set of values into a left-hand side of a system of linear equations with this matrix, right? So that's exactly multiplication of a matrix by a vector. And we write down the answer to our question. So to determine T of, say, vector V, multiply the matrix of T by vector V. Right, so just take the product of a matrix A by the vector V, and so the resulting vector is going to be the image of vector V under this transformation. Now let us look at the following problem. Rotate vector 3, 2, 30 degrees counterclockwise. And determine the result. Now, so let's make a picture. So here we have a vector with coordinates 3, 2, right? So the vector V. And so what we need to do is, so we need to rotate this vector by the angle of 30 degrees, right? And we need to determine, so what is the image of this vector after this rotation. And so the key to solving this problem is not to work with a specific vector, but rather find the matrix of this transformation in general. So matrix of rotation by 30 degrees transformation. Our mantra says that in order to find the matrix of a linear transformation, we need to determine images of basis vectors. So this means that we need to rotate basis vectors by 30 degrees. And so let's start with the first basis vector, 1, 0. So we want to rotate this vector by 30 degrees. So how do we find the coordinates of this vector here? So what we do is, so we note that rotations preserve the length of vectors. So here we had the unit length vector, so this means that the length of the rotated vector is also 1. And then to find its x-coordinate, we drop the perpendicular here, right? And from trigonometry, we know that x-coordinate of this point is cosine of 30 degrees, which is square root of 3 over 2. And the y-coordinate of this point here is equal to sine of 30 degrees. So, and the sine of 30 degrees is equal to 1/2. So this tells us that T of 1, 0 is equal to a vector with coordinates root of 3 over 2 and 1/2. So this is the image of the first basis vector. Now let us look at the second basis vector. So the second basis vector is the vector 0, 1. And we need to rotate this vector 30 degrees counterclockwise. So we're going to get this vector here. So the x-coordinate of this vector is equal to minus sine of 30 degrees. And the y-coordinate here, So this value is going to be cos of 30 degrees. So cos of 30 degrees. And so what we get, well, we can write it here, that t of 0, 1 is, well, sine of 30 degrees is 1/2, so we get negative 1/2 and square root of 3 over 2. And so this allows us to compute the matrix. So the matrix of this transformation is, so we use our mantra. So we place images of basis vectors as columns. So this means that this is our first column, roots of 3 over 2 and 1/2. And our second column is negative 1/2 and roots of 3 over 2. And now we can deal with our specific vector, 3, 2. So if we want to find the image of the vector 3, 2, we need to multiply this matrix. So roots of 3 over 2, negative 1/2, and 1/2 roots of 3 over 2 by our vector 3, 2. And so the result is going to be, so here we get 3 roots of 3 over 2 minus 1. So this is the first component. And the second component is 3/2 plus roots of 3. So we can see here is that this answer is quite non-trivial, right? So it is not possible to guess this answer just from this vector. And so this calculation is rather involved, and it shows the power of this method. So the idea here is that it is way easier to find the images of basis vectors than directly the image of a vector like 3/2. And then once we found images of basis vectors, we obtain the matrix, and then we use our matrix multiplication. So we just multiply the matrix by a vector and get the answer to our problem. Now, since rotation transformations are used very commonly, so let us solve this problem in general. Let us determine the matrix of a rotation transformation by angle phi counterclockwise. Now, in mathematics, the default rotation direction is not clockwise, but the counterclockwise direction. So the point here is that we need to obtain images of basis vectors. So this is our mantra. So whenever we want to find the matrix of a transformation, find images of basis vectors. So this means that we need to find t of 1, 0 and t of 0, 1. And this entails rotating these vectors by the required angle, right? So, well, it's useful to draw a circle here. And so if this is our angle phi, then here we have t of E1, right? And t of E2 will be here, t of E2. So where this is also angle phi. And then from trigonometry, well, this is a unit circle, so this hypotenuse is equal to 1. So from trigonometry, so the x-coordinate here is going to be the cosine of the angle. So we have cos phi. And the y-coordinate is going to be sine of this angle. And for the second basis vector, for E2, so here we see that the x-coordinate is the sine of this angle phi, but with a negative sign. So this is negative sine phi. And the y coordinate is going to be the cos of phi. And so this gives us a rotation matrix So sometimes we're going to call it R phi, and we obtain it by placing images of basis vectors as columns. Cos phi, sine phi, and the second column is minus sine phi, cos phi. And then to calculate images of arbitrary vectors under rotation, so we just multiply this 2 by 2 matrix by a given vector. So since this is such a commonly used matrix, it's a good idea to take a look and remember how it looks like. But generally, so it's a good practice also to not, instead of just stupidly memorizing this matrix, try to remember this diagram and try to be able to determine this matrix just from this simple diagram. If we need to rotate something clockwise, then all we have to do is we take and switch the sign of phi, right? So we use negative angles for clockwise rotation. Now, so far, we considered the case of transformations from Fn to Fm. Now, what if we have a more general case? So how to find the matrix of a transformation T from V to W, where so dimension of V is equal to n, and dimension of W is equal to m, right? So what do we do if our vector spaces are not Fn? So here, so the idea is, so what we need is we need to fix bases. So fix a basis V1 through Vn in V, and W1 through Wm in W. Once we fix bases, we get isomorphisms between V and Fn and W and Fm. And for all practical purposes, we can treat V as the space Fn. Now, what is this isomorphism? So this isomorphism, so this is a one-to-one correspondence between Fn and V is the following. So if we have a vector in Fn, C1, Cn, then it corresponds to a vector in V, which is a linear combination of basis vectors with the given coefficients. And we can go both ways. So if we have a column vector, then we can form this linear combination. If we take an arbitrary vector in V, because this is a basis, we can expand an arbitrary vector in a unique way as a linear combination of basis vectors. And then we associate to any vector in V its n-tuple of coefficients of this linear combination. Now, going back to the matrix of a transformation, our rule remains the same. So what we have to do is to form the matrix of T right? So if we have this transformation, linear transformation from V to W, where we fix the bases in V and bases in W, so compute the coordinates of images of basis vectors. So this means that we want to compute T of V1 up to T of Vn, right? So what we do is, so we take basis vectors in V, we compute the images. So each image is a vector from the space W. And then we take that vector and expand it as a linear combination of basis vectors W1 through Wm. And this gives us an array of coefficients. And so we take this m tuple of coefficients and place it as a column of a matrix. So as columns, as before, right? Okay, so this rule is slightly more complicated, but it's the same rule as before. So the difference between this case and the case of the space Fn and Fm is that in the space Fn, we already have a canonical basis. We have a standard basis that is comes with the space. So if we have a vector space without a basis, then to form matrices, we need to fix a basis. And so then the matrix that we obtain at the end will depend on our choice of the basis. But this is something that we're going to discuss later in this course. Now let us illustrate this with the following example. So let V be the space of quadratic polynomials. So V is the set of expressions ax squared plus bx plus c, where a, b, and c are real numbers. And so we know how to choose a basis in this space. And let's choose a basis that consists of x squared, x, and 1. So what we view this expression as a linear combination, a times x squared plus b times x plus c times 1. So this means that this expression can be thought of via this isomorphism as a column vector ABC. And now let T be a transformation from V to V. So this is a linear transformation of differentiation. So this means that T of applied to a polynomial P is equal to the derivative of this polynomial P prime. And what we want to do is we want to find the matrix of T. Our rule here is that in order to find this matrix, we need to find images of basis vectors. And the basis vectors are x squared, x, and 1. So we need to find T of x squared, right? So our transformation is differentiation. So when we differentiate x squared, the result is 2x. Then T applied to the second basis vector, x, is equal to 1. And T applied to the third basis vector, well, the derivative of constant function 1 is equal to 0. Then what we have to do is we have to think of these as vectors. And we need to think of this as isomorphism, that this space is isomorphic to the space R3, right? And so we need to write down coordinates of this vector in this basis, right? So what are these coordinates? So this is, so 2x can be written as 0 times x squared plus 2 times x plus 0 times 1. And so this means that as a vector, so this becomes a vector 0, 2, 0, right? So these are the coefficients. So to compute the coordinates, we extract coefficients of the expansion of the given vector as a linear combination of basis vectors. So 0x squared plus 2x plus 0 times 1 gives us a column vector 0, 2, 0. So likewise, 1 can be written as 0 times x squared plus 0 times x plus 1 times 1. So this gives us a vector 0, 0, 1. And finally, so this 0 is the vector 0, 0, 0. Having calculated the images of basis vectors and converting them into columns, we can write down our matrix, well, following our rule. So matrix of T is, so A, where, so the first column is 0, 2, 0. The second column is 0, 0, 1. And the third column is 0, 0, 0. Now let us see how we can use this matrix to calculate the derivative. So if we take a polynomial p, which is ax squared plus bx plus c, then using our isomorphism between v and R3, so this is interpreted as a column ABC. So to find the derivative, so what we can do is we can take the matrix of our transformation and multiply it by the column ABC, right? So what's the result? So to find the product of a matrix with a vector, we take dot products of rows with the column vector. So the first dot product is obviously 0. So the second dot product is 2 times A plus 0 times B plus 0 times C. That's 2A. And the last component is going to be 0 times A plus 1 times B plus 0 times C. So this is B, right? And now, again, using our isomorphism with R3, so this is interpreted as 0 times x squared plus 2a times x plus b times 1. And so this is 2ax plus b, right? And that's exactly the derivative of this polynomial, right? Okay, so I wouldn't use this method in a calculus class to differentiate this polynomial, right? But if you need to teach a computer how to differentiate polynomials, then this is a perfectly valid approach for a computer. So it's easier to explain to a computer what the matrix is rather than trying to explain what a derivative is.